So finally, we're going to compare and contrast to try to wrap up and summarize the two things that we've learned, which are basically bimolecular and unimolecular reactions, either as substitutions or as eliminations. And the first thing we should look at are the relative compare and contrast of Sn1 versus Sn2. All right, and Sn1 was the two-step reaction. Okay, that's a two-step reaction where the only thing that mattered in the rate was the formation of the intermediate carbocation. Sn2 reaction, that was only a one-step process with a crowded transition state. All right, and so the consequences of these reaction types mean that in an Sn2 reaction, this one-step reaction really requires everything to get over a big energetic hill at once. So when you have an Sn2 reaction, you have to have, and they tend to favor strong nucleophiles. Whereas in an Sn1 reaction, the nucleophile strength at least doesn't affect the rate. And so the nucleophile strength in an Sn1 reaction tends to matter less. Now, a big consideration on Sn1 and Sn2 are the substrates themselves. And there are two important considerations, and that are the number of substituents on the carbon increases the stability of a carbocation forming, which of course would favor stable carbocations, favor Sn1 reactions. But as you decrease the number of substituents, the bulkiness and the size decrease, which favor that crowded transition state. And so the less steric junk, the more your Sn2 reactions are going to be favored. So you can really think of Sn1 reactions preferring tertiary over secondary systems, with primary systems not doing Sn1 chemistry. Okay, Sn1 chemistry essentially only happening in tertiary and secondary systems, whereas in an Sn2 system, you would expect this to happen for methane and methyl systems, as well as primary and also secondary systems. And tertiary systems don't work. They don't react. All right. So in an Sn2 system, essentially, if you look, what you should see is a strong nucleophile and a uncrowded substrate. In an Sn1 reaction, you should see something that favors the formation of a carbocation, in the sense that, electron donating substituents through hyperconjugation and inductive effects, for instance, tertiary centers and secondary centers. And then the nucleophile actually doesn't have to be that strong, because once you have a nice stable carbocation, anything can come in. Now you'll notice that secondary is listed here both, so probably what I would say, if you see a strong nucleophile and a secondary carbocation or a secondary alkyl halide, you might want to consider an Sn2 reaction. If you see a more modest nucleophile, you may want to consider a Sn1 type reaction. All right. We mentioned the substrate. Now, of course, in a substitution reaction, you're substituting your nucleophile, but you also have a leaving group, all right? And in both cases, you need a good leaving group. It doesn't really matter what, that these both have to have good leaving groups. And so we can draw that down here. We can draw a line through here. And what we're going to say here is both require a good leaving group. And what is a good leaving group? Very simply, both require good leaving group. They are bad bases. So anything that is a bad base is going to be a good nucleophile. The worse the base, the better. So you have iodides and bromides and chlorides. These halides are all pretty good. If you have something that's going to be really stabilized, like a sulfonate, for instance, you can just imagine a lot of distributing, a lot of resonance of that oxygen anion throughout that system. All these things. Or inversely, think of an incredibly, incredibly good acid. Hydroiodic acid, sulfuric acid. The conjugate base of that is going to be a trash base. And so you're going to end up wanting a good acid with a terrible base. Now let's consider solvent. All right. So in this particular instance, a good solvent is going to have to neutralize a charge formation. So Sn1 clearly has charge formation, and when you have charge formation, you have your leaving group is always going to be splitting away from your substrate in an Sn1 reaction. So you're always going to have something that sort of has a feeling of a leaving group coming off, and so you're always going to have that sort of plus and negative thing over here. So Sn1 reactions do have a requirement for a good polar solvent, all right? And so a good polar solvent is going to be one that's going to help stabilize the formation of that species. Now, Sn2 reactions are a bit more ambiguous because you can have that transition state that we illustrated in prior lectures that are polar, and then you can also have a non-polar transition state. And you have to go back and really check that out. But you could have in your 5-member transition state something that is the leaving group is coming off, and that's we can stick with chlorine. That's always going to be a leaving group's going to try to become much more positively charged. That one's going to be always trying to become negative. But you've also got this nucleophile. And if your nucleophile is like an amine, that nitrogen is going to be going from a neutral to a slightly positive charge. But if it is something more like a negative charge, if it's more like a base that's attacking an Sn2 type configuration where it's got a negative charge, that negative charge is, granted, it's becoming less negative, but it's still a partial negative charge, going from a full negative to just a partial negative charge. So in this particular case, solvent selection is ambiguous. So if you see a solvent in an Sn2 reaction, it probably is less meaningful than in an Sn1 reaction. But you really do have to compare the structures that you're forming in the transition state. And conveniently, Sn1 reactions always form a polarized system. Sn2 reactions are a little bit more questionable. Now, now we're going to switch to looking at, so there we go, that's our Sn1 and Sn2. Let's see if I can draw something that sort of makes these look more like a grid. We got something here where those two are the same. Then that goes down here, that looks like that. All right. Now in our E1, E2, now we're going to do E1 versus E2. All right, and in E1 and E2 reaction, the again, a pretty important aspect of E1 and E2 are substrates. So again, we can kind of look up here, although we have nucleophilic, but what we see is that E1 and E2 are governed by Zaitsev's rule. And Zaitsev's rule says that more substituted alkenes are favored. And I introduced Zaitsev in E1, but Zaitsev rule basically works in E2 as well. And so in both cases, E1 and E2 elimination, how did I have that structured here? You can just draw it like that. And then we can draw it like that. But in this case, both tend to favor tertiary over secondary over primary. With primary being unlikely to undergo elimination at all. All right, so Zaitsev's rule tends to be your following your North Star. And of course, you have to be thoughtful with Zaitsev's rule, because Zaitsev's rule is not, it's a rule, and you know, rules are made to be broken from time to time, but that tends to be your favoring component. E1 versus E2, the biggest components, and probably the one that I really should have led off with, is actually the selection of base versus nucleophile. And if you have a good base, then you have a very likely E2 elimination. If your base is trash, then it's probably going to not matter, because again, the key driving force of an E1 elimination is that you form a carbocation to begin with. E2 elimination, bases are super important. So base strength is very important, because just like in your Sn2 particulars up here, you have to have a strong nucleophile in order to get over that single one giant step. Sn1 reactions, your bases are less important, because the first step is a carbocation formation. That deprotonation is actually extremely easy, so essentially base strength is less important. All right, so that is essentially your requirement. You're not going to have an E2 elimination with a weak base. And what are sort of strong bases? Just to recap, strong bases are what you would expect. They would be bad acids. So sodium hydroxide, or your hydroxide systems, your alkoxides, your amides, essentially most things that you can draw negative charge with. And then of course your carbanions are all really good bases. They're all hungry for protons, all right? And in E1 eliminations, of course, all of these will do an elimination as well, but you can also do eliminations with water, you can do eliminations with methanol, because they have lone pairs, right? And you've seen H3O, that's just high hydronium ion that can go off, and you can end up with eliminations that occur in acidic environments, and that works totally fine. Now, one big thing that is very similar to Sn2 reactions. Sn2 reactions have specific geometry requirements, right? They undergo backside attack. E2 eliminations also have specific orientation requirements. And that elimination in an E2 requirement means that you have to have anti-configurations required. And in the E1 reaction, there's less geometric constraints, just like an Sn1 reaction. Now, the big thing to appreciate is that, you know, we've now got sort of our E1 versus our E2, and we've got Sn1 versus Sn2. There's also a competition between each other. Usually it's between Sn1 versus E1 and Sn2 versus E2, or which one you end up forming, but you do have this intra. All four of these reaction conditions can occur, where you can actually have minor products that are substitution products, and major products that are elimination products. So you have E1 versus Sn1 versus Sn2 versus E2 elimination. All right. And then there are just some trends that will help you predict which one you're going to end up going for, right? So weak bases that are good nucleophiles will predominantly give good substitution. So if you have a weak base, but good nucleophile, you will end up with substitution. All right, and good nucleophiles and weak bases, those tend to be big squishy atoms that don't like protons, iodide, bromide. They also tend to be the big squishy atoms in the P block, so your sulfides, your methyl sulfides, methyl selenides, those are also really big. Then you have these sort of really conjugated systems. So azide is something, so that's a negative charge on that. Azide is no interest in protons, really. It's a terrible base, but it is made out of all P blocks, but they're all Sn2 hybridized nitrogens. So they're actually not particularly interested in protons, but they do have a negative charge, and so they will go off and do nucleophilic attack. And you can find that generally with other really conjugated systems. So oftentimes you'll find that carboxylates, for instance, you think of them as bases, but they're really kind of soft. They're not very good bases, but they can do nucleophilic attack. So if you have a substrate, for instance, that looks like this. All right, and then you throw a salt sodium iodide. All right, sodium iodide. Awful base, great nucleophile, pretty unambiguous that you will end up with the iodinated product. Iodine will go kick off the bromine. And that's actually, this iodination is a pretty decent reaction. It's used pretty frequently. I think they say it's Schotten-Bowman reaction. But don't quote me on that. On the other hand, you have that same substrate and you throw in what you think is a great nucleophile, ethoxide. You've actually thrown in a really great base. So you will end up primarily with the elimination product, and that's about at 87% of. But ethoxide is a nucleophile, and so you can end up, and you do end up with a small amount of ethoxide as the substitution product, but that is a much smaller percent. So again, the secondary positions, they tend to be more ambiguous, right? As to whether or not they undergo Sn1 or Sn2 or E1 or E2 reactions. But your primary outcomes are going to be, in this case, if you have a good nucleophile, bad base, substitution. Great base, okay nucleophile, you're going to end up primarily with elimination. Now with methyl halides and primary halides, Sn2 predominates with a strong base. So if this halide, for instance, were instead something like this, you would end up with Sn2 reactions that push that forward. This would be now suddenly more favorable to give you an Sn2 reaction. With tertiary halides, an Sn2 reaction is going to be impossible, and so the only thing that you would have is an elimination reaction. So if you had something like that, your only outcome would be the elimination product. If you had something like that, your most likely outcome, you would have a much more favorable production of the ethoxide being your product, the substitution product, but you would also still get the elimination product as well. All right, because it's just never quite as clean. And so that would be your major product and that would be your minor product. And in this particular case, on a tertiary system, that would be your only product because you're not going to get substitution on that system at all. All right. Now, sterically hindered bases. Now, if this base, instead of being ethoxide, were something much more sterically encumbering, So if we were going to go down here and do something even more drastic, so I just said if we had ethoxide here and we used ethoxide here, that's what we would get. But if we did something with a huge base, we use one of those giant bases that I had talked about previously, then what we would see is much more elimination reactions, because this is a fat, gross base, and it is too fat to be doing some substitution, especially Sn1, Sn2 type chemistry, which is the preferred chemistry. So what you actually end up with, actually this is a real reaction with a real outcome, so I'm going to draw that out there. If you throw in bromobutane, what you end up with is the Hoffman product, where the double bond is terminal. You do end up with just some tiny marginal amount of substitution product, not a whole lot. And this is like 85% to 15%. So with a huge base, you can really flip the outcome here. All right, huge bases, sterically hindered bases, really prefer E2 elimination. So let's just write that down. Huge, powerful bases prefer E2 elimination. All right. So let's summarize these right here. Factors for substituting are factors that prefer which one is more likely. Substitution versus elimination. All right. First, we had discussed base strength. All right, weak bases, and these are pretty weak bases. Those are going to be your halides, your sulfides, your azides. This is going to be, let me just draw this out here so you can see this is things that have lots of pi bonds, those sorts of things. These are going to promote substitution. All right, they're strong, and those are your OHs and your alkoxides and your amides. They're going to promote elimination. All right, so there's one, base strength. Two is all about steric endurance. All right, sterically unhindered things like the methyl, primary alkyl halides, you end up with preferentially substitution. All right, but if you have steric hindrance, and that is branched, secondary, tertiary, you're going to end up preferring elimination. I should be a bit clear here. You have what I would say primary, secondary, and tertiary will undergo elimination. So there's ambiguity in primary carbons there. But steric hindrance is typically one where you prefer less steric hindrance. Substitution is the preferred outcome. And with steric hindrance, branching is particularly advantageous in elimination. All right. And then if you have, say, 3 bulky bases, all right? So if you have bulky bases, or even, so bulky base, right? The sterically unhindered bases are essentially also just, could be nucleophiles. So if you have sterically unhindered bases. All right, what are those? Those are your hydroxides. You know, they're little svelte bases that can get in and grab protons. They can also get in and just do a substitution. So these strong unhindered bases will like to go in and just grab a proton, but they're also just as likely in many cases to do some sort of substitution and kick off. They're small, they can get in, they can do Sn2 chemistry pretty well. Now if you have a sterically hindered base, something like T-butoxide or LDA, lithium diisopropyl amide, your elimination is essentially guaranteed. Or just say that's elimination favored. All right. So what happens if we have, let's just do a couple of things here. We will have that. All right, we're going to call bromopropane. And then we can have a couple of different conditions. We can have sodium cyanide. We can have sodium methoxide. And we can have well, this is usually T-butoxide, potassium T-butoxide, all right? These three different things will give you three different outcomes. Sodium cyanide, we know, is a terrible base, so it's not going to undergo any sort of substitute or deprotonation of anything. It's a good nucleophile, though, because it's a negatively charged carbon, which is going to be a good nucleophile, but it's got a lot of, but it's sp hybridized, so it's not going to be a very good nucleophile. That pretty much assures you're going to end up with some Sn2 reaction where you end up with the cyanide. Sodium methoxide is actually a really great base, but you have a primary bromide. It's right at the very end. So it's both a good base and a good nucleophile, and if you've put the bromide right out there in a totally unsterically hindered position, it's going to undergo an Sn2 reaction, all right? Now, if you move that bromine over to a secondary position, you can see what happens up in the example that I gave up there. But out on the primary ledge, pretty good fodder for an Sn2 reaction. T-butoxide, on the other hand, is just too big to get in there to do any sort of Sn2 reaction, and it's going to exploit its life as a base to give you essentially only the elimination product. It's just not a good reaction for if you're looking for substitution, but it's a great reaction if you're looking for the outcome of a deprotonation. All right. Now, when you start branching stuff, so let's look at another substrate. All right, we've got a branched system here, 1-bromo-2-methyl propane. And let's give two possible reagent scenarios. We can either have sodium iodide, excellent nucleophile, terrible base, or sodium methoxide, excellent base, good nucleophile. In this particular occasion, the nucleophile is going to be able to come in there, probably via an Sn2 type reaction, so that we don't go through a primary carbocation, but you end up with the iodinated substrate there, essentially as your only product. Sodium methoxide, on the other hand, this particular case, is going to serve as a base. It's now two big things, two larger things coming in. So your preferred outcome is now to form the double bond, because you've added a substitution right here, and that makes it different than up here where you have totally unhindered access to a substitution. You've now hindered it by putting it next to a secondary system, plus there's the opportunity to find this secondary alkene. So the elimination reaction is going to principally dominate. All right. Now let's consider secondary halides. Secondary halides are super ambiguous, as I drew up there, so we want to think about what our principal outcomes will be. If we put a secondary halide in a terrible base, ethanol, so it's not really a base. It can be. It's not a base. It's just not a good base. Or you challenge it with something that is a really great nucleophile. Or you challenge it with something that is actually a really great base. Okay. And so in this particular case, your ethanol is principally going to give you your Sn1 type reaction. All right, you're going to end up with the ethoxy substituted product. Ethanol, of course, like water, has lone pairs. It can form a deprotonated product and form the ethonium ion, the ethonium cation. So it's possible that you can have a small amount of elimination product, but this is your major reaction product. The methylthiolate here is going to give you the nucleophilic product. It's going to give you the Sn2 reaction because it's a gangbusters nucleophile and a trash base. Sodium ethoxide, we know it's a good nucleophile, but we also know it's really a better base. And so you're going to end up with the elimination product. Now, when you start getting into really substituted stuff, you're unlikely to see any sort of Sn2 products at all, right? Substitution still favors E2, but does not favor Sn2. So if you have something that looks like this, a really substituted tertiary system, and you just let that soak in ethanol, over time, you would expect to see a substitution reaction that gives you the ethyl ether that comes off there, possibly also the elimination product. Because ethanol, as I said a couple times, not a great base, but you can deprotonate stuff, especially if your first step is the formation of a carbocation. Remember, you first form a carbocation in both E1 and Sn1. That means that it doesn't have to be a good base in order for it to deprotonate and form a double bond. You just have to make a thermodynamically solid product, a stable compound. And a highly substituted alkene is a thermodynamically stable compound. All right. Of course, if you undergo I should erase that because now that's going to be ambiguous. If you throw in a really good base, ethoxide, you will just end up with this. You'll just end up with the elimination product. All right. And the ethanol will give you that as a major product, and that will give you a minor product. But if ethoxide, you only get the E2 product. Okay. So you only get the E2 product. Ethanol, you can get the E1 and the Sn1 product. All right. So let's now try to summarize. All right. So we have different conditions up here, whether you have a type of alkyl halide. All right, you can have methyl. You can have primary. All right. And that can be an unhindered primary or branched. You have a secondary, then you can have a tertiary. All right. And now you're going to have to throw in a nucleophile. Let's say you have a poor nucleophile. And that's going to be like, let's just call it ethanol. All right. Primary methyl with a bad nucleophile, like bromoethane, you're going to get no reaction. All right. A primary, like say methyl, or you have a primary either ethyl, bromide, or something like that, you're going to get no reaction with ethanol. But you're going to get, as you get more branched into the Sn2, you're going to start seeing some Sn1, and you see probably pretty slow, because remember your carbocation is governed, the formation of that, the activation energy is higher in a secondary versus a tertiary, but you're going to see a slow Sn1 E1 reaction. In a tertiary, you're going to see an Sn1 and an E1 reaction, and that will not be as slow. All right. Now, on the other hand, if you have a good nucleophile, all right, and strong base, so these are, for instance, your ethoxides, all right, what you will see in these instances is essentially just a methyl can't do elimination, right? So that has to be an Sn2 reaction. A primary unhindered system is going to end up doing an Sn2 reaction, or a branched primary system is going to give you an E2 system, all right? Secondary system, we have pretty much decided it's there up in the air. We have to look a little bit closer, because it can either be Sn2 or E2. And then you get to a tertiary system where Sn2 is essentially verboten, and you only end up with your E2 elimination. Now, on the other hand, if you have a good nucleophile, so it's a good nucleophile, and it is a strong hindered base. All right, so T-butoxide. Those are excellent nucleophiles. The only time you ever see them act as a nucleophile is on a methyl. So you will get a methyl substitution. So bromomethane will actually do Sn2 chemistry. All of the rest of these are going to undergo elimination reactions. Now there are a couple of properties. Now what distinctly separates mechanisms of Sn1 versus Sn2? What are some of the actual properties of Sn1? So we've got 4 different things that we've discussed. We've discussed Sn2, we discussed Sn1, and we're going to call these properties of mechanisms. We've got E2, we got E1, right? And what were some of the properties that we discussed? So we discussed stereochemical consequences, stereochem. It's a dash. We discussed rate law, all right, and we discussed rearrangements. All right, so in Sn2 chemistry, we said that you have inversion. You have inversion of stereochemistry. Sn1, you tend to have more racemic mixtures from a result. Occasionally, you do have some slight inversion, but principally racemization. E2 eliminations, those have strong requirements with the anti business. We actually call the Anti-Coplanar Arrangement. That essentially makes sure that you have your leaving group and your departing protons have to be away from each other. And both of these are governed by Zaitsev rule to some extent. And that's the rule of the substitution. The better the substitution, the more stable the double bond. Now, rate laws in Sn2 chemistry are going to be rate constants times substrate times the nucleophile concentration. And in Sn1 and E1 reactions, all you're really looking at are the concentrations, rate laws of substrate. E2 It's the same as an Sn1. We still have substrate, except we don't refer to it as a nucleophile. We refer to it as a base, even though that could possibly be the same compound. Okay? And then finally, you have possibilities for rearrangement. And that rearrangement, when you have an Sn2 reaction, no, you don't have rearrangements in Sn2 reactions. You have no rearrangements in E2 reactions. But Sn1 and E1, both because they have an initial carbocation intermediate, they can both undergo rearrangements. So we call that possible. Okay? And that is the review for Sn1E1 and Sn2E2.